Hello, everybody. So we're getting into 15.4 part one today, looking at segment relationships in circles. All right. The first, segment relationship we're going to look at is what's called the chord-chord product theorem. All right. So real quick, go ahead and get the title, and then I'll scroll down for this. Okay. So the chord-chord product theorem. Here's what it looks like. I've kind of color-coded the little I guess we call it a formula, and the chords that are being used. Okay, so go ahead and copy this. If you have, colored pencils or markers, you might want to use them, and then I'll show you what's going on. Okay, so basically, here's the idea of the chord-chord theorem. Okay, maybe the first thing to remind you of is what is a chord? When we have a circle, all right, a chord is just a segment that goes from one edge to the other. All right, so on this, if I were to kind of just highlight it, one of my chords is this one right here. All right, and the idea with the chord-chord theorem, it says that if we multiply together the two parts of this chord, it's going to equal us multiplying the two parts of this chord. All right, so try not to be too thrown off by my color coding, but basically the idea is the two parts of this chord multiplied together equal the two parts of this chord multiplied together. All right, that's the chord-chord product theorem. All right, so that's what we're going to start with. We have another theorem after a few slides, but this is, the first one we're looking at. So let's go ahead and try an example on this. Go ahead and copy this slide, and we'll try it together. Okay, so this is asking us to find segment KI. Okay, so maybe the first thing to realize, segment KI is this entire chord. Okay, to figure out what this entire chord is, well, we know one part of it. We know this part of it's 6. We need to figure out the other part of it, right? And then we can add them together. So really, the main part of this question is, what is X? All right, well, here's what we know. We know that if we multiply together the two parts of this chord, it's going to be equal to us multiplying the two parts of this chord. Okay, so let's go ahead and do that. I'm going to start by multiplying the two parts of this chord KI. So 6 times X. And I know that's going to be equal to me multiplying the two parts of this chord of JH, which is 9 times 8. Okay, and here is my really simple formula. I can solve this and get what X equals. All right, so 6 times X is 6X, 9 times 7 is 72. All right, solving for X, get rid of 6 by dividing, and 6 goes into 72 12 times. So we get X equals 12. Okay, and it's really that simple. There it is. Okay, so that's what's kind of cool about this theorem here. If you ever have two chords crossing, multiply their parts, set them equal, you can find missing pieces of them. Okay, so I'm gonna have you guys try one of these on your own. Oh, actually, hold up. I kind of got a little ahead of myself, right? That they didn't ask for X. They didn't ask for that. They asked for KI. So this isn't actually our answer. Let's go one more step and let's point out that segment KI, the entire chord, is going to equal, 6 plus 12. All right, so it looks like KI is going to equal 18. Okay. So yeah, be careful with making that mistake. Some of these might ask for just X. Some of them might want the entire chord. It really just depends. All right. Okay, so now with that, let's have you guys try one of these out. This one's asking you to find segment AB, which is this entire chord right here. So a lot like the last problem, you need to first figure out what X equals and then add these together to get AB. Okay, so go ahead and try it out. All right, so I know the two parts of this chord, 3 times X, is going to equal the two parts of this chord multiplied together. I guess I'll make a different color, 6 times 2. All right, and yeah, once you get this out, pretty easy problem. Looks like we're getting 3x equals 12. Divide both sides by 3. 3 goes into 12 4 times. All right, be careful. Just like that last problem, it might be tempting to make the same mistake I made and think, sweet, there's my answer. But no, they want all of AB. So let's point out that segment AB is going to equal 3 plus x, which we figured out was 4. So it looks like AB equals 7. Okay, cool. So that is the chord product. Let's see if we're moving on. Let's do one more of these that actually has some weirder values, and then I think we'll get into the other theorem we have to look at today. So go ahead and copy this one. We'll do it together. Okay, so this one wants us to just find x. All right, just to kind of highlight it, there's one of my chords. There's another one of my chords. All right, weirder values, but let's go ahead and do this math and see what happens. Let's start by multiplying the two parts of this red chord together. So I'm going to do x times x plus 4. Okay, here's the thing. X needs to be multiplied by all of x plus 4. So I need to put that in parentheses like this. Okay, and that's going to equal multiplying the two parts of this chord, x plus 2 times x plus 1. The best way to write this is probably like this, x plus 2 times x plus 1. Okay, so just one thing, if you ever have multiple terms in one of your, I guess, measurements, put parentheses around it. Okay, so now we have a lot of distribution to do here. Let's go ahead and start by distributing our x value on the left here. So x times x is x squared. X times 4 is a positive 4x. Okay, over on the right, we need to distribute both of these. All right, so we're going to distribute the x into this parentheses. And then after that, we're going to distribute the 2 into the parentheses. Okay, but let's start with the x. X times x is x squared. X times 1 is a positive 1x. Moving on to 2, 2 times x is a positive 2x. 2 times 1 is a positive 2. Okay, so some weird values here. Here's a couple things I know I'm going to do. First thing, I've got some like terms. I can combine this 1x and a 2x and get a 3x. Okay, so I'll do that on the next step. But let's also do another thing. I know that I have these x squareds that are on opposite sides of my equal sign. I need to get them to the same side. I need to start getting all of my x values to the same side. So what I'm going to do is I'm also going to subtract this x squared over to the left-hand side. Okay, here's the good news. Because I'm doing this, x squared minus x squared, those are eliminated, and these are also eliminated. So it's nice our x squared, or I guess you can think of it as our quadratic, has been eliminated. We don't have to deal with it on this problem. All right. So on the right here, I have a 4x, or sorry, on the left, I have a 4x. On the right, I'm going to combine those and I'm going to get a 3x, and then I have that plus 2. Okay, now, fairly simple problem. I still have x's on both sides. I'm going to worry about that first. I'm going to bring the 3x over to the left. So I'm going to subtract the 3x from both sides. 4x minus 3x gives me 1x, or x. On the right, I just have 2. And there it is, x equals 2. Okay, so this just threw in some more difficult algebra, something maybe we haven't seen in a little while. But again, the good news on this was that these quadratics, these x squareds, were eliminated. If they weren't eliminated, this would be a lot more difficult problem. This would require a lot more out of us. Okay, but on today, on these problems, I'm fairly certain that quadratic is going to be eliminated always. Okay, so with that, let's move on to our next theorem. And this one is called the secant-secant product theorem. Okay, so go ahead and get this slide here, get this formula down here. It's a really important one. Okay, so first thing, secant. We haven't actually seen what a secant line is. All right, all a secant line is, if I were to just draw a circle, a secant line is a line that goes through a circle. Okay, that it's not just ending on the edges, it's going through it. Okay, so that's a secant line. This would be a secant line, and that's basically what's going on right here. These lines are going through. Okay, so that's all secant means. All right, but here's the formula. If you guys notice, this looks a lot like the formula for our chord theorem, but there's a fundamental difference to it. Let's figure out what it is. Okay, first thing, they're saying we're doing EA times EB. Okay, first thing to notice, EA is this portion outside the circle. Okay, so we're taking that part of our segment and we're multiplying it times EB. Here's the big thing. EB is not this portion of our segment. That's AB. EB is the entire segment. Okay, so I don't know if you want to put something like that or maybe color code it. all right, if you're using colors, but EB is the entire segment, the whole thing, or if you wanted to like maybe highlight it like this, however you want to represent it. Okay, and it's the same time, or it's the same idea here. EC is the segment outside the circle times ED, which is the entire segment. Okay, maybe I'll make that blue. Okay, so that's the big thing. Be careful on these problems. You're going to be tempted to go, oh, EC times CD, just like we did with the chords. You know, this piece times this piece. No, it's this outer piece times the entire thing. Okay, so that's what's the difference between this and the chord. So let's try this out. Okay, go ahead and copy this. We'll try it together. Okay, so we're just asked to find X. All right, so let's go ahead and start with this segment here. Here's what I know. I'm going to multiply this outer segment, AB, so that's 5, times the entire segment, this entire line. Careful, the entire line is not X. It is X plus 5, right? Those two segments added together is the entire thing. So X plus 5. Okay, so that is going to equal me doing it with the same secant line here, taking the outer portion, which is a 6, and multiplying it times the entire segment. Okay, the entire segment, be careful, is not 7, it is 6 plus 7. All right, which we could add those together and get a 13, but I'm going to put 6 plus 7 in here just so in your notes you can really understand, you know, where we're getting a 13 from on the next step. Okay, so now we have, you know, our equation. That's the hard part from here. It's pretty simple algebra. So I'm going to distribute my 5 into the parentheses. I'm also going to combine my 6 and the 7. So 5 times x is 5x. 5 times 5 is 25. Okay, over on the right, 6 plus 7 is 13. And if we want to just do this all together, 13 times 6 is going to give me 78. So let's do those two steps together just to save us, you know, an extra step. Okay, from here, we're going to go ahead and just start solving for x, right? So first thing, deal with addition or subtraction. I'm going to get rid of 25. So I got 5x equals 78 minus 25 gives me 53. And dividing both sides by 5. Looks like I'm getting x equals 53 divided by 5. I could leave that as a ratio, as a fraction, but I'm going to ask that you guys actually divide these and get a decimal so we can get a number that actually makes sense. So 53 divided by 5 is going to give me a 10.6. Okay, and by the way, when we do these, we'll continue to round to the nearest tenths, but there's no other numbers past this, so it's just going to say, you know, 10.6. Okay, so yeah, there it is. Just, you know, be careful. Don't do 5 times x equals 6 times 7. That's not the way these work. All right, so I'm going to have you guys go ahead and try out one of these secant lines, and then try out another one of these chord theorem problems. Okay, so go ahead and do both of these, and then we'll look them over. All right, so on number 1 here, the first thing I would start with, normally I start with the one that has the variable in it. So I would start with this secant line. So I know I'm going to take this outer segment, 3, and I'm going to multiply it times the entire secant line, which is not x, it's x plus 3. Okay, now I'm going to set that equal to doing the same thing with this secant line, the outer segment, 6, times the entire line, which is not 9, it's 9 plus 6, which I'm just going to do and go ahead and write that as 15. Okay, that's the hard part. Make sure your first step looks like mine, or maybe you had a second step where you added these together, but make sure you added these two pieces together to get these entire segments. Okay, so yeah, let's go ahead and just do this real quick. 3 times x is a 3x, 3 times 3 is a 9. Over here, 6 times 15 gives me 90. All right, and then just two-step equation, subtract 9, and then we'll divide by the 3. All right, so it looks like we're getting 3x equals 81 And let's see, 81 divided by 3 is going to get me 27. So I'm just going to put it off to the side here. X equals 27. Okay, so yeah, there's number 1. Let's take a look at number 2. All right, number 2, first thing to notice is that this is 2 chords crossing one another. Okay, this is the chord-chord theorem. All right, so we know on the chord-chord theorem, this is the one that's more straightforward. If I'm looking at this chord, I'm going to start with this one. I'm multiplying the 2 parts of this chord together. So I'm going to do 3 times x. Okay. And I'm going to set that equal to me multiplying the 2 parts of this chord together, 4 times 4. Or sorry, 4 times 6, not 4. All right, so yeah, way more straightforward. 3 times x is 3x. 4 times 6 is 24. Okay, dividing both sides by 3. 3 is going to go into 24, 8 times? So it looks like x equals 8. Okay, so yeah, these are not terribly difficult. Just try not to get them mixed up. The secant problems are definitely the weirder of the two. So be careful on those. All right, guys. So yeah, that's that for today. I'll see you in class. Bye.